Hi, thanks for the introduction and thanks for inviting me. I'm really happy to be here and also really happy that my flight from Boston was able to land this morning despite all the wind. It was a little rough, but we made it. So, by the way, can everyone hear me in the back? Yes? Okay, I'll try to project. So, I want to talk to you about my work on connecting vision and language. And in particular, this is going to be a talk about deep learning and neural networks, and how do we design neural networks that are learning to connect vision and language in an end-to-end manner. So I'll definitely explain in a lot more detail what I mean by that. So first of all, since most of you are language researchers, and I am mostly a vision researcher, and I often pretend to be a language researcher. So I wanted to motivate a little bit why I think it's important to connect these two fields. So traditionally, people have worked on problems in vision, and separately there was a separate group of researchers that worked on problems in language. But more and more recently, there's been interest in some cross-border rating and also in deeper ways of combining the two problems. And I really think they're very complementary. So, in vision, I think that if we don't connect it to language, and in particular language semantics, then we're really handicapping ourselves. And I'll give you an example what I mean by semantics. So if we know about this object, and we know that it's a soccer ball, then we see this new object, and without any linguistic connection of what the meaning of this new object is to the one we know about, we really have no way of knowing that they're similar things. You can use both of them for to play with, but they look fairly different. So just based on vision features, it's not clear that those two objects are actually related. So on the other hand, in language, I think I'd like to argue that language is handicapped without vision because a lot of concepts in language are grounded in perception. For example, if you wanted to define this word cute, and you could look in the dictionary and it will say this definition, attractive in a pretty or endearing way. Then you say, okay, but what's attractive or what's pretty? And if you look in the dictionary for those words, you eventually have some kind of cycle, right? It will probably say cute. But if you can ground it in something visual, like this little video or an image, then it can make it easier to, sort of understand what the meaning is behind some of these concepts. So another question that skeptics might ask is, well, why do we need to combine vision and language? Why not just treat language as something that gives us categories? So we have categories or words that define different visual concepts. Like, given this image, we could just train a system, let's say a neural network, to recognize what are the categories of visual concepts in that image. And so it would just give us a list of things like flower, field, sky, and clouds. So some skeptics might say, well, why not just do that? And then that's vision, and why do we need anything else? So I want to show you this example. So imagine you had a vision system that could do this category detection, and it told you in some image that I'm not showing you the image, but I'm just showing you the output of that system, and it says there's a giraffe, there's a zebra. So I want you to try and imagine what that image looks like. What do you think it looks like? And now I'm going to show you the image. How many people imagine that? Okay, I'm impressed. So clearly just having a list of categories isn't a rich enough description of what's happening in this image and certainly many, many images. So what I would argue is that it'd be better if we could describe this image in language, in a sentence, let's say. We could say, there's a zebra sitting on top of a giraffe, or we can make it more descriptive and say it's maybe like climbed to the top of the giraffe's neck and it's hanging on for dear life. We could describe that it's a sunny day and so on. So there's a much richer way to output language based on this image. So with that kind of motivation, I wanted to briefly describe some of the work that I have done and with my co-authors and collaborators we've done on connecting vision and language with neural networks. So just for a bit of background, in this first task that I already alluded to, the task of image captioning, we have a picture and we want to describe it. We want to describe what's in the picture. And there was some very interesting early work on this task of image captioning. For example, Ali Farhadi's paper at ECCV 10 on kind of going beyond just single labels. So you have an image and you're trying to now predict a triplet of categories where there's an animal, stand, and ground. So there's some kind of subject, verb, and object triplet that you're trying to predict. And then there was very influential work from Tamara Berg's group, which they called Baby Talk. And so this was the first paper that really tried to predict captions for images. And it kind of, as you could see, it was quite limited. It was using template models and filling in objects and verbs in those templates. So it would say things like, there are one cow and one sky. So they called it Baby Talk because it kind of, didn't sound like a grown-up human was talking. So this was before deep learning, and then in 2015 roughly, or late 14, neural models were introduced for this task, and they were, I think, around 8 papers in CVPR that year on kind of image captioning with a neural model. So this was our work that was part of this group of papers. And so now you can see that if we use a neural model to do this image captioning task, you get much more fluent captions, so you don't get this baby talk anymore, right? So it says things like a brown bear standing on top of a lush green field, or a person holding a cell phone in their hand. And you also see that they're much richer sentences. So you have kind of details like holding, not just holding a cell phone, but holding in their hand. And you kind of say, wow, that's amazing. How did the model recognize the hand? There's kind of a very small part of the image that even, that is the hand in that image. So so this was really cool and very impressive and very exciting. And basically the key insight behind these kinds of models, neural models for image captioning, were very similar to, and in fact inspired by, neural machine translation, right? So probably most of you are familiar with neural machine translation, where we have an input sentence and we want to predict the output sentence in the target language. And the way they work is there's a recurrent neural network encoder that encodes the input sentence, such as English, into some hidden state representation. So there's some fixed size vector of numbers, a continuous vector that now represents the meaning essentially of that sentence. And then there is a decoder that translates it and outputs one word at a time the output target sentence in French. So so this model was introduced in 2014 by Sutskever et al. And it was very successful for machine translation. It can also add things like attention and various bells and whistles there, but this is the basic approach. And what basically we and our colleagues realized is that you could treat an image as essentially a different language. And if you do that, now you replace your English sentence or whatever your source sentence with an image. You encode it, you represent it with some hidden vector that represents all of the objects and visual concepts in that image, and then you decode it into a sentence. So that's essentially what this early neural image captioning work was doing. So now, if you have a video, you could also do the same thing. So this was work we did for NACL 15, where now we're taking a video, encoding it also into a fixed vector, and decoding it into a sentence. And of course, you need training data of the form of images paired with sentences or videos paired with sentences. But if you have such training data and you have it in abundance, then you can learn very powerful models. Now, the encoder I showed you so far is just basically a convolutional neural network. But if you have more than one frame, so here we're kind of cheating by averaging over all of the encodings of all the frames. But you could also do this where you actually extract all the frames and encode each one first with a convolutional network, and then you encode the sequence with an RNN. So it becomes a sequence-to-sequence problem. So that's kind of the key insight behind how most vision and language models, I would say, still work for the most part, although I'll tell you about a kind of a different approach today. But first I want to kind of briefly show you some results of what happens if we apply this kind of model to vision and language tasks, right? So again, it's a neural encoder decoder model. There's some input. The input is encoded into some fixed vectors, and the vector is decoded into the output. And you could frame all of these tasks and solve it with this kind of model. So there's image captioning, which I already talked about. There's also visual question answering. I'll show you some referring expression grounding results, which you can also do with this kind of model. Video captioning, and I'll also talk about dense video captioning, which is where you have a long video and you want to caption it densely as opposed to just a single clip where you want to produce one caption. So, I already showed you some results of image captioning. So let me show you a few more results from these tasks. This is visual question answering. So we have an input image and an input question. So a sentence that represents a question, like here the question is, what is the child standing on? And the goal, the task, is to predict the answer. And the answer could be a sentence, or in most current data sets, it's just a single word or maybe a pair of words. And in this case, the answer is skateboard. So you could do a similar thing. This particular model, is a little bit more complex in that it's actually based on a memory network. If you don't know what that is, it's just basically kind of like an encoder decoder, but it has some attention built into it. So it's trying to line up the words in the sentence to particular areas in the image. So you could do this. You can train a neural model, or you can even train a simple LSTM encoder decoder model as well. The difference is now you have an additional input. In addition to the image input, you also have the question. So you need to encode the question as well, but as long as you can encode the question and the image features, then you can predict the answer. Then for a slightly different task called referring expressions, what we want to do here is, given a query and an image, localize the object or the region of the image that the query describes. So in this example, the query is lady in black shirt, and this is the output of our model. The green box is the output of our model. The yellow box is the correct box that was provided by a human annotator. So here's another example. Here the query is fence window left of center door. And again, this green box is the output of our model, and yellow is the ground truth. So you can see it's pretty good. It's a pretty good localization. So here we're not captioning and we're not answering questions, but we're kind of answering a question of the form of where is this, right? Where this is no longer just a single category. Like, we're not just saying detect all windows or detect all people. Now we want to detect things that are defined by the sentence or the referring expression. And now if we change the query to window upper right, then the system returns a different region, which is what we want. So this is a good example of the model working as it should. And then we also had some work on video captioning, which, as I mentioned, now it's similar to the image captioning problem, but we have a sequence of frames. So I think this should work. So we have an input video now with a sequence of frames. And for now, we're just assuming that the video is trimmed, meaning that there's one activity in that video that we want to caption. And later, in a couple of slides, I'll show you an extension to when we don't have a trimmed video and we just have a long video we want to caption. So here, we assume that we can describe in just one sentence what's happening. We're extracting frames and encoding them with a convolutional network, which then we take the last layer output of the convolutional network, feed it into the recurrent LSTM, and it has 2 layers. Once all the frames are encoded, we start decoding into the caption sentence. So in this case, the caption sentence is "a man is talking." So again, it's very similar to neural empty. I'll show you some examples. Maybe the audio will play.
An egg.
Okay, sort of played it. Basically said a woman is making an egg. So this is...
People are dancing. Bicycle.
Should actually say a man is
riding a bicycle.
A man is riding a bicycle. It's getting cut off a little bit. So you get the idea. So the nice thing about this approach, yes?
So the question I have is, when describing a video, I could have one sentence for each frame.
Mm-hmm.
I could have one sentence for the whole video. Or I could have a story, a sequence of events that are happening in the video. So how can you define which problem you're tackling and maybe how does these architecture could handle the 3 of them?
Yeah, that's a very good question. And these are all perfectly valid problem statements. I would say that if this model is primarily evaluated on the task of captioning a video in one sentence. So basically what the model needs to learn is what is the main activity, and there could be multiple ways of describing, and there could also be something happening in the background. But the model needs to select what's the main activity, and then it needs to, describe it in a sentence. But if you could also, and we have done this, you could train it in very similar way to describe each single frame as its own, like what's happening in this frame, what's happening in the next frame.
And how do you handle the fact that there could be multiple correct answers, multiple ways of describing the sentence?
Yes. So actually, it's a very good point. If you ask humans to annotate these videos, you get extreme variety. Actually, this particular corpus was produced from taking YouTube clips, and they were actually they were collecting a paraphrasing corpus, so they were throwing the videos away. But we thought it was really nice for this video captioning problem. But the idea was that you could, if you show humans a short video, they could describe it, and they would actually paraphrase what's happening in many ways, and they do. And there's I don't have a slide here, but many different ways of saying the same thing. And right now we're basically training the model with some sort of average log likelihood loss on all the training captions, and it sort of learns to caption probably the most frequent caption that humans provide, but it does learn a variety of ways of captioning too. But there's no specific way in this model that sort of deals with the variability.
I guess in the example of the example of the caption, and not just say people moving around. The training set had people dancing, so that's really what defines the sentence, I guess, or not. So the training set, I guess, defines what is really the action, the verbs, or the objects.
Right. And what we find is actually that even though this is now a much more fluent model. When we evaluate these sentences using Blue and Meteor and all the standard metrics, they're much higher than what we had with earlier template models. But in many ways, they're also limited. They tend to overfit to certain biases in the training data. So for example, if you show a video to the model that has kitchen or some kind of cooking activity, most likely will say a woman is something. So it's learned from its training data that that's a likely way to start the sentence if you see some kind of cooking activity happening. So so they're definitely, even though they're, sorry? It could be, but the model just learns to, fit to the training data and the most likely thing. Sorry. Did you have a question?
Have you done any work in terms of extending it from short video clips to be able to turn video captioning into longer clips?
Yes, we have very recently extended this to caption longer video sequences, and I'll talk about that. Yeah, just a couple more slides. Maybe just one. So we've evaluated this on other kinds of video captioning data. This is a different data set called MSR VTT, and it's a video to text data set. Again, these are fairly short clips. I would say on the average maybe 15 seconds long. But they cover a variety of activities, and it's really a difficult problem for the reasons that were already mentioned. Like there's a lot of variability in what someone could describe or how they could describe a particular video. A woman giving a speech on a news channel, but you can think of many other ways to describe this. Did you have a question?
Just quickly, yeah. It seems like many of these can be described by a single frame from the entire video clip. So I don't know if you have any comments about that, about the necessity for these clips of multiple frames. Is it really learning something different than from a single image?
Yeah, so that's a good point. Because of the nature of this data, the differences are not very large between different frames. And actually, the differences in activities are largely due to kind of what the objects are in the background. So this is something to do with basketball, but if you had a whole data set of basketball videos, you wanted to do some fine-grained description, it would be a slightly different problem. But here the model could just learn, if I see a basketball court, I'll just say something like a basketball team is playing, and it's probably going to get a pretty good Meteor score. But sometimes the frames are not all useful. So if you knew the right frame, it could probably do pretty well compared to using all the frames. But sometimes just seeing multiple frames and aggregating information over those frames improves the score. And in fact, it does work better if you use multiple frames instead of one. We also applied it to movies. So they're feature-length movies. There's a data set of 200 movies, and you could train this model to generate descriptions of everything that's happening on screen. So this is actually data from the visual description service, which is an extra audio channel if you rent a DVD or if you stream a movie. It sometimes has this extra channel where there's a trained human annotator who's describing everything that's happening for people who are visually impaired. And so this data set comes from transcribing these descriptions, and then we can train these models to do this automatically. And the performance there is not as good as on these simpler YouTube domain. Okay, so I want to talk in a little bit more detail about one particular approach that we developed recently for video captioning, in particular for dense video captioning. So this was the question that you asked earlier. What if we have a longer video? So if we had a longer video, now we can't exactly apply this model that I just described, this encoder-decoder model, because there are multiple activities going on, and we want to now caption each of the activities separately. So this is a segment of a longer video that I'm showing you from a data set that we were using. And, I'm showing you for each activity the beginning and end, this whole segment, and the corresponding caption. So a female weightlifter bends at the knees, and then the next caption is she lifts a barbell to her chest, and you see the corresponding temporal segment, and then she lifts it over her head before dropping it heavily to the ground. And you'll notice here right away that there actually may be different ways to generate these descriptions here in terms of which activities you group together, which ones you separate, right? So I could have just as easily said, she lifts a barbell to her chest and then lifts it over her head, and that would be the end of that activity. And then I could say, and then she drops it heavily to the ground, right? So how you segment the activities temporally is actually quite ambiguous, right? So that adds to the complexity of the task. So this task is called dense video captioning. It was introduced by Krishna et al. In the ICCV 17 paper that you see here. And they also introduced a data set. They collected a data set of these kinds of temporal annotations of activities and their corresponding captions. And this data set is based on ActivityNet, which is a large-scale data set of YouTube video of different kinds of activities. So they also proposed a way to solve this task that involves essentially having a network that predicts the start and end of each activity, and then having another network that encodes now that temporal window of frames and decodes them into a caption. But the problem with their approach is that this temporal segmentation stage, it's also called the proposal stage because we're proposing likely activities that we would want to describe. This temporal segmentation stage and the captioning stage are separate, and they're not trained in an end-to-end way. And end-to-end training is really powerful because what it does is it lets errors be propagated all the way from the caption words all the way down to, the input through the whole pipeline. So in this case, because it's not end-to-end, that means that errors in sentence prediction can't be propagated back to this temporal segmentation or temporal proposal generation, right? So you have to train the temporal proposal generation separately, and then based on the output of that piece of it, you train the captioning model as if kind of a captioning model that assumes that it's already given trimmed temporal subsequences. But if you think about this task, how we segment the video into activities actually should affect the kind of captions that we generate, right? As I was saying earlier, I could instead, extend this one to be a little bit longer. But if I extend it a little bit too long, and then I don't update my caption, then the activity doesn't correspond well to the actual caption. So what we did is we proposed a way to do this dense video captioning task in an end-to-end manner. So kind of the overall system is described here. There's a lot going on, so I'll go through it in a little bit of detail. And I want to, okay, there's a clock there, good. I want to make sure I don't run out of time. So we have an input video, and this is a long video. I think we're only now limited by the size of memory in terms of how long the video we can load. And so our network, this one big neural network, but it's separated into two stages, the proposal stage and the captioning stage. So the proposal stage takes the input video and applies a convolutional neural network. This is actually a 3D convolutional neural network called C3D. And it's just what it sounds like. It's just a convolutional network that is extended to the temporal dimensions. So it's 3-dimensional instead of 2-dimensional. So it applies filters in a continuous way. So we just kind of slide it across the whole video, and it encodes the video into some feature maps. And then we take some layer of those feature maps and feed it into the segment proposal network. So this piece of the network, basically, its job is to make proposals of where an activity is starting and ending. And so it has to propose these activities, and it also has to predict, is it an actual activity or is it some background thing? So it's trained in this binary way of, is it a foreground activity or not? So once this segment proposal network has predicted proposal segments, then these are passed along to the captioning module. And this module is doing two things. First of all, it's taking features, these convolutional 3D features that were extracted from the video. It's taking these features from the predicted temporal proposals, so it's only looking at the conv features that are inside that temporal proposal predicted by this network, and it's pooling them within that temporal segment. So it's doing 3D segment of interest pooling. And this gives it a fixed vector, basically a feature vector, that represents that particular temporal proposal. Okay, so this is now it gets a list of these proposal features for different proposals. Each one has a fixed size vector after this pooling stage. And this is fed into a captioning module. And this is just a recurrent LSTM that takes the teeth proposal and generates a caption for that teeth proposal. Okay, and so this continues for all of the proposals predicted from the segment proposal network. So at the end, from the first proposal, let's say the captioning module generated this sentence, she lifts a barbell to her chest. And then for the second proposal, it generated the next sentence, and so on. And there's one more piece that I didn't describe, which is this hierarchical step. So intuitively, when you're captioning a whole video, those captions are not completely independent, right? They should depend on the previous context. So, for example, if the model said a female weightlifter is on stage, and then the next sentence, it should say she as opposed to he, right? So there is context in these sentences that they're depending on each other. So this is why we have this additional module. In the captioning module, we have this additional LSTM, which we call the controller LSTM. And so this network, essentially its job is to keep track of the context of the whole video and the previously generated sentences and provide that context to the next sentence, to the captioning module when it captions the next sentence, when it captions the next temporal segment. So it takes the video context, which we get just by max pooling all of the C3D features across the whole video. So that gives us this video context feature vector. And it also takes this SPT minus 1, so this is actually the previous sentence, the previously predicted sentence for proposal T minus 1. And then it updates its hidden state, and it provides that hidden state to the captioner LSTM for the next proposal. Yes?
Two questions. The first one is, the proposals are purely temporal or spatiotemporal?
Yeah, no, the proposals are purely temporal.
And the second one is that when defining the LSTMs, the seamless case, right, is at every frame you have a space and you capture the transitions from frame to frame. But here, one could envision this happening from each temporal segment to another temporal segment. The temporal segments could overlap. And some of the LSTMs are more on the language side, so then it could be from a whole sentence to a whole sentence, or to can you describe a little bit more the temporal scales at which the LSTMs are operating?
So in terms of temporal scales, the captioner LSTM operates at the scale of each proposal, and the proposals are just maybe 10, 15 seconds long. And by the way, these proposals or the temporal activities can overlap. So we're not restricting the model to kind of segment, into non-overlapping proposals. They can actually overlap. So it could start one sentence and then it could start another one before it finishes the first one. And then the controller LSTM operates over the entire video, so it's encoding all of the sentences in that were produced for that video. So it could be potentially a very long sequence of sentences. I think in this particular data set, I forget what the average number of sentences, but it's more than a few. It's potentially quite long. Question?
So the segmentation is latent. It's not part of the evaluation nor part of the training objective, is that right? So you just get scored based on the likelihood of the text that you're outputting?
No, so I actually didn't mention this, but yes, it's a good question. So these temporal segments are actually given a training time because, at least for the data sets we have, they are annotated with the start and end time for each. So each sentence has the right segment that's annotated. So we actually do have a loss on this segment proposal network. So it's trained with a binary loss, which says, did I predict the segment correctly as a foreground segment as opposed to a background segment? And also has a regression loss on the start and end time.
So that may answer my other question, which was why you got away from the RNN, the first convolutional and then RNN encoding, so the sequence-to-sequence sort of thing that you described earlier. I guess it's so that you can take advantage of the supervision on the proposal boundaries. Is that the motivation?
Yeah, so we wanted to take advantage of that, although you could still have an RNN, an encoder-decoder, that predicts, that based on its hidden state, predicts the start and end boundaries. However, what we wanted to do was we wanted to not just predict the start and end boundaries, but we wanted to then pull the features from that predicted segment, as opposed to use the hidden state of the network. There are probably other ways of implementing it, but we actually took this part from an existing model we had that does activity detection. And it was also very efficient. It can run at something like 1,000 frames per second. And it's very similar, if you're familiar with faster RCNN for object detection, it's very similar in spirit to that. But yeah, there are other ways of implementing things. Okay, lots of hands going up.
So, to follow on the comment you just made, and I was thinking in terms of a combination of the referring expression and the local video. So can you comment on how you would be able to localize in time a specific activity that you're looking at in hours or, say, surveillance video?
Right, so this model doesn't do that, but it is a good problem. So basically what you would do is something like referring expression grounding, but now you have a very long video as opposed to a single image. And it's a harder problem. We're actually working on that, but you still need this ability to localize temporally and potentially also spatially, actually. If you have video where there are multiple activities going on, let's say you have surveillance video, there could be something happening over here, something else happening over here. So you also need to find not only temporal but spatial boundaries. And then you also need to evaluate the query against that proposed segment or spatiotemporal segment and predict kind of the score of how well it matches. Question? I'm sorry, I didn't hear.
Is there any reason why thinking of analysis pipeline in this way can make it easy or can make it useful to answer that kind of question.
To answer the question of how well it's performing?
How well the weightlifter lifter.
Oh, I see. How well the weightlifter is performing.
Right.
I see. It's an interesting question. I haven't really thought about it. I mean, right now we're just focusing on generating the sentences and scoring the sentences, but you could define some other task. And it's actually a good question. How do you evaluate these vision and language questions, especially captioning models? Like, what's the point of just generating a caption? So, as was suggested, you could use it for query retrieval, so you could search a very large database for certain kinds of activities, or you could do something else like evaluate their performance or something like that. Okay, so I'm going to try to skip maybe all this. This is just showing you detail of how each thing works. It's not that important. So we evaluated this on the ActivityNet data set. So this is the top table. It's kind of ugly, has lots of things, but basically these are blue scores, Meteor, Cider, and Rouge. So these are all standard kind of generation metrics. And then we compared to the Krishna et al. Model. They also have a version with context. So we compared to both no context and context. And you can see, for example, on Meteor, first of all, the thing to notice is that the scores are very low. So this is a difficult task. And so Meteor, for example, goes from 3.7 to 4.8 with context. And then with our best model, it goes to 8.5. So it's a significant increase, but it's still a pretty low Meteor score. And I'll show you some qualitative examples so you get a feeling for how well this is performing. And we also evaluated on a different data set called TACO's multi-level. And I'll show you an example from that data set next. So here the overall scores are better because the data set is easier. So it's not kind of this huge variety of things from YouTube, but rather it's a single kitchen scene where someone is cooking. Question?
Do I need to compare against the same model with equivalence temporal proposal, or just equivalence without any temporal information?
We did evaluate the proposal stage separately. I'm not showing that here.
I want to understand how the actual temporal information compares subsequent captions.
Yeah, so that's what I'm saying is we have that evaluation in the paper. I'm not showing it here. I don't remember exactly, but it's it does improve with end-to-end training, which is something that we really wanted to look at. But I can just maybe show you some examples, and that will make it clear. Yeah, I apologize, I don't have that table in this slide deck. Okay, so this is from the TACO's multi-level data set from MPI. So you'll see the description down here. Maybe it's a little small. It says the person opened a drawer. The person took a cutting board and knife out of the drawer. The person, something with a knife. Person opened the refrigerator. I can't keep up with it. Okay, now it's so here nothing. The person took a cucumber from the refrigerator, placed the cucumber on the cutting board, removed the leaves. Cut off the stem, remove the leaves. Remove the leaves from the cutting board. So you can see that it's confusing this, I think it's a leek, with a cucumber. So that's one of the problems with this data set is that the objects are very small, and actually most of the visual features you get are from the background, which aren't changing very much. Wash the herbs in the sink. So the model it has learned to recognize different parts of the scene, like that there's a sink and a cutting board and the fridge. Sometimes it confuses the small objects like cucumber versus herbs. Okay, now it thinks it's a leek, finally. It's the person washed the leek. And you can see that this is all from one video. It actually goes on for quite a while. Person cut the end off the leek. So in this data set, there are different subjects, different people. Now it's a pineapple. It's recognizing the cutting action. And it's also segmenting, temporally segmenting actions and finding what are interesting actions. But yeah, now, so clearly the visual features, especially for these small objects, are one of the problems to still tackle here. Okay, so let me stop this and show you a different one. So this is from the ActivityNet data set. And again, I apologize, it's very small. So I'm going to try to keep up and read what it's saying. So a person seen walking down a gym with a large group of people on the side. They recognize the gym. The man then jumps into the air and begins to jump around the mat. The man then jumps off the mat and walks away. So this one's interesting. You can really see the limitation of the model because there are actually clearly interesting things happening, but it's not saying anything yet. And then it says the man is shown on the field. Okay, arguably that wasn't the most interesting thing about what you just saw. And the man is showing running in the field. So it's kind of being very generic here. Like ideally, we'd want it to recognize the actual sport that's being played. And sometimes it does. But this is a much more difficult data set. So I think there's going to be more sports. So in ActivityNet, there are quite a few sports. The man then walks away, and the camera pans around the camera. So that's an error, obviously. But it is learning to say things like, and the man then, right? Because it's learning that there's a sequence of events. A woman is seen standing in a stage and leads into her performing a routine. The girl then does a routine and flips on the beam. So it's recognized that there's a beam. It recognizes that there's, something like some words specific to gymnastics or performing. But it's not saying things in a very fine-grained way, but it's getting kind of the main gist of what's happening. So this is all one long segment that the model predicted, basically. And then she then flips her routine and then jumps off the beam. So presumably she's going to jump if the model predicted this correctly. So again, you see here a very long temporal segment that was detected and described in this one sentence. Okay, she didn't actually jump yet. Maybe I can speed this along. Okay. So the conclusion is clearly the deep neural networks are great.
Yeah, one quick thing. If we just try to break down probably the group of entities in the entity has periodicity in them, and the entity does not have the periodicity in them. For instance, looking into the action when it was repeating in the last video, there is a movement of pattern, and it's a repetitive movement of the pattern, right? So, would you like to show some parts, like overall in the entire data set, if you just want you to find out that what are the activities, or just I would say like if we want to find out the activities which have the periodicity activity in them, and we probably could learn on a small subset of a video rather than showing like a bunch of information, like the whole video sequence, for example. Like in the sport, there is a periodic movement, and you can see that one. The same in the type of walk.
So what do you mean by periodic movement? What do you mean?
The repetition of the same movement again and again, like walking with the same step rather than in the pattern. So for that, I don't need a whole video sequence. You eventually learn from a subset, which is a static,
Right. Yeah, that's an interesting point. That So this model is actually it's supposed to learn to segment the activity, but as you said, some activities are very periodic. So like walking, like when did I stop walking? I'm still walking, or did I start again, right? So the model is having to kind of in an artificial way basically find, okay, this is when it starts and ends. So yeah, I agree. That's a limitation of this approach, and we should think about better ways of kind of building that into the model, that it should know, okay, this is just a repetitive activity. I'm just going to say something, and then I'm just going to be silent because it's the same activity happening. And we don't know if it's actually implicitly learning that, but there's nothing explicit that's forcing it to. Okay, so I believe I'm supposed to stop at 1. Is that right? Do I have a few more minutes? Few more minutes, okay. Okay, so in the few minutes I have left, I wanted to kind of end by motivating another part of my talk that I won't get to, but I wanted to kind of, first of all, conclude by saying that, okay, neural networks are clearly great. We can do all these difficult tasks with some degree of success. Obviously, they're not perfect. But, you know, there's a lot of excitement about them, and, you know, you might kind of think that they can do anything, but what I would argue is that there are some very important limitations, and especially when it comes to language and vision. One problem with neural networks is that they're very black box, right? So you have some video input that goes into some giant soup of neurons, and the sentence comes out on the other side, and you don't know what happened in the middle. And what I'm really interested in is, and some other people are as well, is understanding what the model is doing and kind of building more interpretability into it, or post hoc trying to interpret what is the decision-making process that's happening in these large encoder-decoder models that have hundreds of millions of parameters potentially. And, you know, the reason that we may want this is because, you know, especially if we use these models for critical tasks like self-driving cars, or maybe, you know, something where the end user wants to know that they can trust the system. And also we may want to correct it. For example, you know, why did it not recognize cricket? Did it just not learn what cricket bats look like, or something like that? Then we could maybe correct it. And then finally, because actually language is very compositional, but these models are just one solid kind of block, and you know, they're not really parsing the language, they're not kind of decomposing it into subtasks, and this especially is important for question answering. So I just want to show you a little bit of a preview for this work that we're calling it explainable AI, where we want to understand what is the model thinking about. You know, maybe it predicted this caption because, you know, it saw a person and it saw that the person has long hair, and that's why it said a woman. Or maybe it just learned that, you know, I see a kitchen and there must be a woman in there because that's what I've seen in my training data. So we'd like to have the ability to explain this thought process behind the model. And then for question answering, you know, questions are kind of, they can be very open-ended, very different, right? And intuitively, how would you answer a question like this? What is behind the foot of the bed? You would probably try to decompose it into some subtasks, right? You would try to find the bed, and then you would try to find the foot of the bed, and then look what's behind it, and then describe that thing. And this is still a pretty simple question, but you know, I can show you a more complicated one down here. So we have some work basically trying to explain what these networks are looking at when they're describing videos, and also here. So this is a more complicated question. You know, you can still think of how to decompose it into steps, right? So there should be maybe a separate subroutine that just finds the green mat ball, and then another one that looks for all things that are the same size as that, and then counts them, right? So this is work with some folks at Berkeley, and this paper called Learning to Reason with End-to-End Neural Module Networks that tries to build an end-to-end model that is still end-to-end, so it has the power of a end-to-end neural model, but it breaks up the task into subroutines that actually implements each task as a separate neural network. So here, after breaking it up into these kind of this program, as you can think of this as a program, each of the subroutines in that program are implemented as a small neural network, and their inputs and outputs are chained together, and then finally it produces the answer. So the advantage here is that you can actually understand what the model is doing a little bit better, hopefully, because you can, first of all, you can see what's the sequence of modules that the network is using to solve the problem. And you can also visualize for each module what were the inputs and outputs. So for find, I'll just show you a quick example for find. For this example, the network predicted that the green mat ball should be the input to the find module. So you can see that it's actually looking for that thing in the image as a first step. And then you can see the output of that, and you see, okay, I actually did find the green mat ball. So that makes sense. So this makes the model more interpretable, and you know, I don't have much time to talk about this in more detail, but I invite you, if you're interested, to look at the paper. And I thank you for your attention. Oh, the title, yeah. I'll put it up. Yeah. There was a question back there?
Yeah, multitasking. So that seems somehow related to interpretability. And I wonder if you want a system to do multiple things, so you're doing captioning, but you might also want to do other things with the image. Does it help those other tasks if you learn how to caption? Could you get, if you're trying to do other things with either the visual or the language, how well do they interact and show representation?
Yeah, so multitasking and actually compositionality is a big problem with, it's a big issue with neural models. They're not inherently compositional, and they're not inherently multitask. And I think it's a very important question to study, actually. What happens is if you train a neural network to detect objects and just say, like, this is a cat, this is a banana, this is a car, and it's learned to do that for 1,000 categories, and it does it very accurately, and then you go and train it as part of a captioning network on some captioning data. It learns to say, you know, this is a monkey sitting in a tree eating a banana, but it doesn't see certain words. It's going to forget them. So there's this problem of catastrophic forgetting. So they're not inherently compositional models. So we need to really come up with ways to make them compositional and make them so that they can learn from multiple tasks and compose that knowledge. There is some work on this, actually, that's promising.
I was specifically about a multitask objective, where the same weights are asked to do many tasks at once and to sum the live loss or task loss from several tasks. I'm just curious whether that helps in your in the part of the space that you've been working on. It helps in some other parts.
Yeah, it does actually help. So for this captioning novel objects problem, it does help, in fact. It helps a lot. Because it avoids the problem of this catastrophic forgetting, as opposed to sequential training where the network forgets the old task. Yeah.